So we're going to continue with the review at this point. We're on side 4, the skateboard problem. It says a skateboarder speeds up from rest to a velocity of 9 meters per second in 15 seconds. It speeds up with uniform acceleration. So first we're going to draw a skateboarder. So I'm going to put this skateboarder on a hill because that's what would cause it to speed up. And so there's our skateboarder, and we'll put it on a hill and say that the starting position is 0 meters, and let's say down and to the right is a positive direction. We also have to list the given information. 9 meters per second represents the final velocity, or the velocity at 15 seconds. Our change in time, or final clock reading, is 15 seconds, but there's one other thing in here that is hidden in here a little with the words from rest. And that means the velocity at time 0 is 0 meters per second. And then they're going to ask us what to find later. It says draw a qualitative motion map to represent the motion of the skateboarder. Because the skateboarder is speeding up from rest, we want to start with the dots close to each other and getting further and further apart. A total of 5 dots is what they request. 1, 2, 3, that's 4. We'll go with that. We can make those even bigger. We'll have 1 dot apart, 2 dot apart, 3 dot apart, 4 dot apart. And there's no velocity on the first dot because it's moving from rest. Then we have a small velocity vector. Notice I made the first one 1 hash mark long, 2 hash mark long, 3 hash mark long. Did I count these correctly? And then 1, 2, 3, 4 hash marks long. And our acceleration will be constant. And these should all be the same size, because for the positive change in velocity, that's a positive acceleration. So while the acceleration vectors are all the same length, the velocity vectors have to get longer and longer. Next up, we just need the shape of a position versus time graph. And we've had the wheel and axle lab and the speeding up, slowing down lab, so we know this is going to end up with a top open curve for our position versus time graph. For your velocity versus time graph, we need to make it quantitatively accurate. Now, our biggest velocity is 9 meters per second, and our biggest clock reading is 15. Let's take care of the clock readings first. We have 1, 2, 3, 4, 5, 6, 7, 8 seconds on our 8 hash marks on here. If we make this 2 seconds apiece, 2, 4, 6, 8, 10, that's going to make 15 seconds right in between these last two, 15 seconds. And then we have 1, 2, 3, 4, 5. If 9 meters per second, we should probably multiply 2's on here as well. 2, 4, 6. And the top one will be 10 meters per second. This will be 8 meters per second, which means our 9 meters per second is actually going to be right in between the two of those. That should be right between the 8 and the 10, 9 meters per second. So if we're starting at rest, our starting velocity is going to be 0. And at the 15-second mark, our velocity is going to be 9 meters per second. And then we want to draw a line from there. If you have got 2 pencils, maybe you could use the edge of your pencil to draw that out. You can put that on there and we'll be good to go. What's the acceleration of your skateboarder? Well, we know the calculate acceleration. We need to do change in velocity divided by our change in time. So if our initial velocity was 0 and now it's 9 meters per second, we have 9 meters per second, and that took us 15 seconds to speed up. 9/15, I think, is 6.6 meters per second squared, I think is the math on that. Let's see, that'd be 3/5. Yeah, that's 0.6. All right, I should have brought a calculator with me. How far will the skateboarder travel in these 15 seconds? So now we want to find displacement. You can actually do this 2 ways. The way we did it in class is to find the area under the triangle. So if I drew this down here and we wanted to find the area of the triangle, we can say that the area of the triangle is equal to 1/2 the height times the base, which is the displacement. And the displacement is 1/2. The height of the triangle is the final velocity times the change in time. So 1/2 the velocity final was 9 meters per second. 15 seconds. And we know that half of 9 is 4.5, and 15 times 4.5 is 67.5 meters. The other way you could have solved this, and it would have been equally correct, is you could do change of position equals 1/2 the acceleration times the time squared plus the starting position, but our starting position is 0. And if you plug that in, you got 1/2 the acceleration is 0.6 meters per second squared times our clock reading squared, which is 15 seconds. Now, it doesn't look like I'm going to have space to write out, but order of operations, we wanted to square 15 seconds first, and 15 times 15 is 2 1/4, 225. And you multiply that by 1/2, you multiply that by 0.6, and you still get 67.5 meters. So you get the same answer either way. Our last question for this is how fast will the skateboarder be moving at the 11-second mark? To do that, we need final velocity is equal to the acceleration times the time plus the starting velocity, but the starting velocity is 0. You guys have already calculated the acceleration at 0.6 meters per second squared times the clock reading of 11 seconds. And we know 6 times 11 would be 66, so 0.6 times 11 would be 6.6. Seconds cancel out here, and so that seconds squared over there, and we end up with 6.6 meters per second would be the velocity at the 11-second mark. So that takes care of the skateboarder problem. You also did one of these for homework. I've put an additional problem down here. It says, how would the problem look different if the skateboarder was already moving at 8 meters per second and slowed down uniformly to a stop over 10 seconds? You could resolve all of these with that same problem, and that would be some more good practice for you. If anybody had questions about that, we could talk about that before we take the test on Wednesday. I hope that helps.